Hello all, welcome to the session. In this particular session, we are going to see the recently concluded paper, that is GATE 2022 solutions. And here we are going to discuss the fluid mechanics solution, that is a part of a subset of the aerodynamics. Now coming to the weightage and the question pattern, let's see. So here we have totally 5 questions that we are asked in recently concluded paper, in which 1 mark question were 2 and the 2 mark question were 3. And the total weightage, if we just say total marks allotted to this particular fluid mechanics in this particular year is 8 marks. Now, so before moving on to the section segments, we are going to start our session from very basic questions that has been asked in this particular paper. So first question that you are going to see is basically this question is also no, if you just ask me the marks, that marks that is allotted to this particular question is what? 1 marks. Now coming to the solution of this particular thing, consider a steady 2-dimensional incompressible flow over the non-porous flat plate as shown in the figure for the control volume PQRS. Let me again just draw the control volume, this one PQRS. So these are nothing but the control volume. The speed that is being given u infinite at the section PQ is uniform, and the speed at the RS is given by something equation, right? Where n is nothing but a positive integer, that is whatever the exponent is there, that is nothing but a what? Positive integer. The value of A naught they are asking, for which the flow through the section PS will vanish. So it's a very simple and very basic question, but for that we need to understand something that already been discussed in the class of the fluid mechanics that we have seen in the boundary layer theory, right? So first of all, we have to note it down the equation. E of y is given as A naught pi by h to the power n. Now we need to find the values of A naught such that there should not be any flow through this particular PS section, right? Now, so to understand the solution for this question, let me just take you through the basics. This is nothing but a flat plate, first of all. This flat plate we are having, in which we are having, let's suppose that the length is L. Width, suppose they have not given in the problem. Yes, width is not given, so you can take W or unit, whatever it may be, automatically it will cancel out. So you should not worry that much. Now, in this particular flat plate, the flow is happening. Initially, it is happening at some velocity called U infinity, right? With the call U infinity, the velocity, the air is approaching towards this particular flat plate, which is non-porous, means there is no hole at all, so that the flow cannot happen in the transverse down direction. Now, in this one, you know that if I just draw only the portion of this flat plate, initially, whatever the velocity profile is there, that is a uniform. U infinity. But after that, what happens? The velocity profile is getting what? Changes to this one. Maybe parabola kind of thing, right? Now, but why it is happening? You know that because of boundary layer formation, it is getting the shape of this particular thing. And here we have what? If you just take this section PQRS. So here it's what? A control volume. If I just draw, so it's a PQRS. From the fluid mechanics, if I just go through the basics of the boundary layer theory, you know that whatever the mass flow rate is there through the section PQ, if I just calculate the mass flow rate through the section PQ, it will be coming out to be what? Rho into U infinity into the height they have given is what? H. H into what? Width. What is the width? W. W is nothing but what? Width of the plate. Width of the plate that is in the perpendicular to the plane of the paper. So that is the mass flow rate that is happening through PQ segment. Now, what is the mass flow rate through this particular section RS? If you just calculate rho into, we have to do the integration because now the velocity profile is what? Velocity is not constant. So we have to do the integration. U of y is given at given as a naught into y by h to the power n, right? So what will be the integration? Rho into u into dy. I'm just taking the one element which are there at a distance of y, which is having a particular gap of what? Dy, right? So that is what we have to do the integration. Rho of u into dy, right, from 0 to h, from 0 to h. Now, again, what we need to do, and you know that because of the boundary layer formation, if I just give the concept of boundary layer formation, if I just give the concept of boundary layer formation, you know that through the flat plate, initially the velocity profile will be linear one. Initially, the velocity profile will be linear one. But after that, due to boundary layer formation, the velocity profile will no longer be linear one. Velocity profile will no longer will be linear one. Right? Now, because why? Because whatever the deficit is there, the complete flow area is not been occupied. This much of area is what? Deficit. Right? The velocity is what? Getting reduced. You can say that area will be same, but the see whatever the mass flow rate through this segment, this is section 1-1. What is the mass flow rate through this section? Suppose that 10 kilogram per second. But what happens due to the boundary layer formation, the velocity will be what? Getting reduced. And because of that, the mass flow rate, suppose that if I'm going to take the section 2-2, the mass flow rate through this section will be 7 kilogram per second. I'm just saying for example. Now, whatever the deficit in the mass flow rate, that has to be compensated by flowing through this particular segment like this. And that's why we have studied the displacement thickness, right? To compensate this 3 kilogram per second, because you know that in the fluid mechanics, the mass conservation has to be satisfied everywhere, irrespective of the nature of the problem or the matter of the concern for us. The mass conservation has to be satisfied everywhere. Remember like this, right? So now, if you just balance it out, mass flow rate through section 1-1, that will be equal to mass flow rate through section 2-2 plus additional mass flow rate that has to be taken place through the section what? If I just take section 3-3, right? That is what we have mass conservation, and that has to be satisfied everywhere. The same concept we are going to apply over here also. Whatever the mass flow rate through section PQ will be there, that has to be equal to mass flow rate through section RS plus mass flow rate through section what? PS. Mass flow rate through section RS plus mass flow rate through section what? PS. But in the problem, they have mentioned that the mass flow rate through section PS is what? 0. So you should not bother about these things, right? So directly what we need to do, we need to just equate the mass flow rate through section what? PQ. That has to be equal to what? The mass flow rate through section RS, right? So here mass flow rate through section PQ, what we can write? Mass flow rate through section PQ, that must be equal to RS. Mass flow rate through section PQ, that must be equal to mass flow rate through section RS. What are the mass flow rate through section PQ? Rho into U infinity into H into width, that is equal to rho into U of Y dy into width from 0 to H. This will cancel out. This will also cancel out. So U infinity into H, that must be equal to, what are the U of Y? U of Y we have in terms of A naught will be Y by H to the power N. So that we are going to put into the integration, and we are going to do the integration Y by H to the power N dy from 0 to H. So that thing we are doing here. A naught, sorry, h to the power n, h to the power n, yn plus 1 divided by n plus 1 from 0 to h, u infinity into h, a naught divided by h naught, h to the power n plus 1, h to the power n plus 1. So finally, what will be the a naught? U infinity into n plus 1, because other things will cancel out. So these are the adjustment for this particular a naught, right? So if you just go through, so this will be your final answer. Now, if you just go through your options, so option B will be correct, right? So that is the answer for question number 16. Now, moving on to the next section, next question, that is 17th question. Now here, consider the velocity distribution u of y as shown in the figure for the two adjacent fluid layers L1, L2. What they are asking, the viscous forces that has been exerted by the liquid layer L1 onto the liquid layer L2, right? You know that whenever the two fluid layers, they are in the motion, so definitely they are going to exert some kind of opposite forces onto each other. It is just happening because of what? One property called as viscosity, right? And because of that, the viscous forces will be generated onto the each fluid layer, and that we are going to explore onto the next page. So let me just give some basic idea about this question. Now, first of all, you need to identify where the fluid motion is happening actually, right? So now if you just consider the plate, let's suppose that two plates are there. The bottom plate is fixed one, and the upper plate is moving, let's suppose that moving with some velocity called v. And in between that, we have the fluid. Suppose that in between we have the fluid. In between, we have the fluids. Now, whenever the motion will happen, what will happen? Each and every fluid layer will try to oppose the motion of other fluid layer or above fluid layer. Now, if I just take the velocity profile, suppose something like this. I'm assuming that the velocity profile is parabola. For example, it's not guaranteed that we are getting always parabola. I'm just saying for the sake of example, the velocity profile in between the gap of the two plate, in which one plate is moving and other plate is what? Fixed. Such a type of flow we call Qubit flow, right? Now in this particular segment, suppose that this is the layer 1, layer 2, and this is nothing but the layer 1, number 1. At this situation, what will happen? L2 is trying to moving what? In which direction? In this direction. Now L1, if I just try to exaggerate, suppose that this is the fluid layer L2 and this is the fluid layer L1. What the fluid layer L2 or what the fluid layer L1 will do onto the L2, it will try to apply the force in this direction. It will try to apply the force in this direction. What the L2 will do? L2 will try to oppose the motion of fluid layer L1 and it will try to exert the force in this direction. Right? So this is the force F of S which is being exerted by L1 onto the L2 fluid layer. And this is nothing but the force. Suppose that this is nothing but Fs 2 onto the 1, and this is the Fs force which are happening. I'm just writing again once again. F of S that is being exerted by the fluid layer number 1 onto the 2. Right? So you got the idea that, sir, in this segment, in this way, we have to proceed ahead for the question that has been mentioned in the 17th one. Try to observe. The situation is not very similar that I have given the example here, over here. The situation is something different. It might be possible that it is happening between the two flat plate, in which one plate is what? Fixed, and other plate is what? Moving with some velocity v. That may be the possibility. And in this segment, again, they have taken the velocity profile to be what? Parabola, something like this. In doing so, what will happen? This is nothing but the fluid layer L1. And this is what we have the fluid layer. Suppose that this is the fluid layer L2. What they are asking the problem? For the two adjacent fluid layer L1 and L2, the viscous forces exerted by the L1 onto the L2 will be what, right? So this is what we have, the L1 fluid layer, and this is what we have, L2 fluid layer. They are asking what will be the viscous force direction onto the fluid layer L2 by the L1. See, L2 will be trying to moving in which direction? In positive X direction. So what will be opposite force exerted by L1 onto the L2 fluid? Will be what? In this direction. So that is a very simple problem. They ask that what will be the direction of viscous forces exerted by the L1 onto the L2 fluid layer to the left, right? So this is what very small, very basic fundamental thing. Even if you just gone through the two block in the engineering mechanics, block on block problem, and suppose that we have applied the force V to this one, or force F to this particular lower block or upper block, you might have gone through the different types of, the frictional forces that has been generated onto the surfaces of the block. If you just have the fundamental understanding of those things, this problem looks very easy when you just compare to the what engineering mechanics problems, right? Now, let us move to the next problem that has been asked from the dimensional analysis and similarity. Now, in this problem, just try to observe the problem. A cylindrical object of diameter 900 mm. They have given the diameter. They have given the diameter. They have given the diameter is designed to move axially in the air. That means what? This is a prototype, and the prototype has been observed in the what? Air medium. And this prototype is moving with some velocity called 60 meters per second. Its drag is estimated on geometrically half-scale model in water. That means whatever the model has been prepared, the model has been tested in the what? Not in the air. It has been tested in the what? Water. Assuming the flow similarity. See, for flow similarity, you know that three conditions must be satisfied: dynamic similarity, kinematic similarity, and what? Geometric similarity. Now, even though if you just satisfy the condition called dynamic similarity, no need to satisfy the condition, or means whatever the conditions of kinematic and geometric similarity will be there, that already being what? Satisfied. If you just satisfy the term called dynamic similarity. Right. Now, what is the dynamic similarity and all the kinds of stuff that has been given in the course very beautifully. Right. Now, even this similar problem has been asked 2 times before in the same aerospace, I think 2017 as well as what 2018. Right. So now they have given the property of the fluids in the air and water, something like this. They are asking that if the model drag force has been given as 2280 Newton, what will be the drag force on prototype? Simply they are asking these things, right? Now, so first of all, we will categorize in 2 segments: prototype and model. The prototype has been tested in the what? Air. The model has been tested in the what? Water. Right? Now, so U infinity or U of prototype, simply I can say that 60 meters per second they have given in the problem. Right? They have given in the problem. And other property called such that mu of P is given as what? Something called 1.01 into 10 power minus 3 Pascal second. The density of the air will be given as 1.2 kilogram per meter cube. Again, if you just take the model, U of model, the velocity of the model, that has not been given. That has not been given, right? There's some purpose why they have not given, right? Now, mu of M, I think you know that 1.86 into 10 power minus 5 Pascal second, that has been given in the problem, of course. Rho of model, they have given no need, right? 1000 kilogram per meter cube. I think mistakenly we have taken the dynamic viscosity for the air, they have given 1.86. So it's, changes will be there. So here it will be 1.01. Here it will be 1.01 into 10 power minus 3. No. Here it will be 1.01 into 10 power minus 3. And here it is 1.86. Here it will be 1.86. into 10 power minus 5 Pascal second. Right. So these are the things that has been given in the problem. Right. Let me check once again. For the water they have given, for the air they have given something like this. Correct. First of all, you should know the meaning of dynamic similarity. If you don't understand the meaning of this thing, you cannot proceed ahead. The dynamic similarity means, listen very carefully, the ratio of two different forces at the corresponding or of the corresponding points of model and prototype should be same. Again, I'm writing this thing also. The ratio of two different forces of corresponding points of model and prototype should be same. My dear friend, what is the meaning of this? You know that we have in the nature, we have what? So many forces: inertia force, viscous force, and what? Pressure force, gravity force. So many forces are there, right? What they are saying, suppose that if you just consider any forces, let's suppose that inertia force you are considering, then inertia force of the model and inertia force of the prototype, that will be equal to what? Viscous force of the model, viscous force of the prototype. Even it will be equal to what? Pressure force of the model, pressure force of the prototype. In doing so, if you just write inertia force to the viscous force of the model, or simply, I will not confuse you, simply I will write what? Inertia force of the model divided by viscous force of the model. I'm just taking this term to the what? Left hand side, and this term to the what? Right hand side. So what you are going to get it? If you just compare these terms, what you call? You call what? A Reynolds number. What is the Reynolds number? Reynolds number is basically what? It's a ratio of the inertia force to the viscous force. It's a ratio of the what? Inertia force to the what? Viscous force. Right? What is the inertia force we have? Rho into L square into V square. L is nothing but characteristic dimension. For flat plate, it will be L. But basically, if you just write for what? If you just write for what? For tube, it will be what? Diameter. And the viscous force is what? Viscous force, we just try to calculate tau into A. So I'm writing what? Mu into V by L into what? L square, LC square. So what I'm writing, mu into V into what? LC. This will be the viscous force. So now if you just calculate the Reynolds number, I'm not calculating, I'm just writing. So what will be the inertia force? Rho into L square V square divided by what? Mu into V into L. So all the terms will cancel out. So what you are going to get it? Rho into L into V by what? Mu. This will be the formula for the what? Reynolds number, my dear friend. This will be the formula for what? Reynolds number. Now, why I'm doing so many things? Because here we can write Reynolds number of model that has to be equal to what? Reynolds number of prototype. Whatever the Reynolds number of the model will be there, that has to be equal to what? Reynolds number of the prototype. In doing so, we are going to calculate the velocity of the model. Because without calculation of the velocity of the model, you cannot calculate the drag force on prototype. Because suppose that if you just want to calculate the drag force on the prototype, you just need to calculate either inertia force or the viscous force, but you don't know the velocity, right? If you just don't know the velocity, how can you calculate the inertia force or the viscous force or any forces, right? So here what we can write, even though you're calculating the drag force on the model and prototype, indirectly that will be equal to what? Inertia forces only. So either you calculate inertia force or the viscous force, that doesn't make the sense. Automatically it will be same thing, right? So either of the formula, use it and you can just calculate the what? Forces. But before that, we need to just equate what? Reynolds number of the model that has to be equal to Reynolds number of the prototype. And for that, I'm just removing some of the part. So these are the very basic thing that we learned in the course called fluid mechanics, in which the subtopic is what? Dimensional analysis and similarity, right? So these are the very fundamental things, but very, very important thing. Now, here only I'm just calculating the, by these things, rho of model, d of model, v of model, divided by what? Mu of model. Why I'm writing characteristic dimension? Because we are just taking what? Just read the problem. Cylindrical object. Cylindrical object means what? Tube or pipe, in which the characteristic dimension or length will be what? Diameter, not the length. So rho p into dp into vp divided by what? Mu p. Now, if you just put the formula, right, whatever the data has been given, if you just put it out and if you just calculate the velocity of the model, you will be calculating, you will be getting something called 7.819 meter per second. The moment you just calculate these things, you can just calculate what? The ratio of the viscous force of the prototype to the viscous force of the what? Model. And if you just calculate the mu into v into L by this particular formula, so what you are writing, mu p into vp into dp. And of course, what is the dm by dp? What is the diameter of the model as well as diameter of the prototype? They mention in the problem very clearly, half scale. That means what? dm by dp will be what? 1/2. They directly mention, right? So this thing you should not forget. So mu m into vm into dm. Now further, what you can write, mu p that has been given in the problem, that is 1.86. Let me just remove this part. Let me just remove this particular part. So mu p will be what? 1.86 into 10 power minus 5. Vp will be what? 60. dp is what? dp by dm will be what? 2. What about mu m that has been given 1.01 into 10 power minus 3. Vm that has been given, that already being calculated at 7.819, and dm, you know that 1, because 2 by 1 directly we have taken. Now, so if you just calculate it by this one, the viscous force on the prototype, you will be getting what? Because viscous force on the model they have given, that is what? 2280. This thing they have given in the problem. So if you just calculate, you'll be getting what? 644 Newton. That means option B is correct. All the data has been given to you, right? I just forgot to mention this particular data. Now, if you just combine this one, all the data has been given in the problem, put the value and get the answer. That is what the thing has to be done in the examination, right? Now, moving to the next question. A rotational velocity flow field they have given in the problem. Rotational velocity flow field is given in the problem, something v is equal to ay plus bxj. That means it is a two-dimensional flow field in which the constant a and b value has been given. The air density has been given in the problem. They are asking what is the pressure value at the location x equal to 6 meter and y equal to 8 meter, right? And we have to round up to what? Nearest integer. Now, so first of all, we need to write the velocity vector field. So velocity vector field, they have given again ay plus bxj. That means in simply we can just say u component will be ay and v component will be bx, right? And the pressure value they have given at the location x equal to 0, y equal to 0, something called 0, right? So we have to use the momentum equation. So first of all, we have to write the x momentum equation. What are the x momentum equation? U into dou u by dou x plus v into dou u by dou y plus omega into dou u by dou z plus dou u by dou t, that has to be equal to 1 minus 1 upon rho dou p by dou x plus viscous term. What is the viscous term? We are going to have it. What is the viscous term? We are going to have it. We are going to have the viscous term as nu dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. These are the terms that we need to find it out from this particular x momentum equation. Right? Now, where nu is nothing but what? Kinematic viscosity. So first of all, we need to calculate dou u by dou x. What is the dou u by dou x? 0. What is the dou u by dou y? It's a. A value is what? 10. B value is what? 20 per second. Right? Now, what is the dou square u by dou x square? It's a 0. What is the dou square u by dou y square? It's again 0. What is the dou u by dou z? It's 0. And again dou u by dou t. There is a no time term. It will be 0. Put the value. What you are going to get it? U will be 0. Sorry, you will be having the value called ay. Dou u by dou x is 0. So this term will be what? 0. This term will be what? 0. This term will be what? 0. This term will only this particular term will only be there. So ay. A is what? 10 into y. Dou u by dou y will be what? A. What is the a? 10. Just wait. V is what? Bx, right? V is nothing but what? Bx. So it will be what? B. See, V is nothing but what? 20 into x. And what about dou u by dou y? Dou u by dou y is what? A. A is what? 10. So minus 1 upon rho. Again, all this term will be what? 0. All this term will be 0 because dou square u by dou z square will also be 0. Will also be 0, my dear friend, right? So minus 1 upon rho, dou p by dou x. Rho is what? 1. Rho is what? 1 given in the problem. So if you just integrate it, so what you are going to get pressure as minus 100 x square plus some constant C1. That is my first equation, my dear friend. Right? Now again, you are going to write the y momentum equation. You do not bother about the z momentum equation because we are dealing with the two-dimensional flow field, right? So y momentum equation, if you just use it, so what you are going to get? U into dou v by dou x plus v into dou u by dou y plus omega into dou v by dou z plus dou v by dou t. That has to be equal to minus 1 upon rho dou p by dou y plus nu into dou square v by dou x square, dou square nu by dou y square, dou square nu by dou z square, right? And again, if you just calculate, so this term will be 0 because what is the dou u by dou t? Dou u by dou t will be 0. This term will also be 0. What about this term? Will also be 0 because there is a no y term in the v component. So we have left with the what? 10 into y. Dou v by dou x is what? B, that is 20. That must be equal to minus dou p by dou y. Now if you perform the integration, what you are going to get the pressure value as minus 100 into y square plus C2. That is my second equation. That is my second equation, my dear friend. If you just combine equation number 1 and equation number 2, so what you are going to get it? Minus 100 x square minus 100 y square. C1 plus C2, that will together will become another constant. I'm just giving right to some name, C3. At x equal to 0 and y equal to 0, they given in the problem, the pressure value is what? 100 kilopascal. They have given in the problem very clearly, right? So by that, you will be calculating C3 as minus 100 kilopascal. C3, they have given minus 100 kilopascal. Now, once you calculate the C3 value and putting into the equation, the final equation I'm writing over here, minus 100 into x square minus 100 into y square minus 100 into 1000. So that together it will become what? Pascal. All together it will become what? Pascal. So what is the pressure value? We have to calculate at 6 meter, 36, 100 into y, 64, minus 100 into 1000. So what is the pressure value? If you just calculate, you'll be getting what? 90,000. Pascal. But we have to remember that we have to calculate in kilopascal. So it will be 90 kilopascal. So what will be the answer? 90 kilopascal will be the answer for this particular question, right? So that's a very fundamental question based on the conservation of, like we have the equation conservation of mass. Similarly, we have what? Conservation of momentum. And similarly, what we have the energy equation. So based on our momentum equation, this particular question has been framed, right? Moving on to the last question for this particular set, that is, this particular fluid mechanics section. Consider a solid cylinder which is housed inside the another cylinder that is fixed one. That means one cylinder is there. Inside that we have the another cylinder, and this cylinder has been rotating, kind of what you can say the bearing one. Inside the bearing we have what? Shaft that has been rotating, and in between that we have the liquids like this. And now this particular cylinder has been rotating with some RPM. Even in fact, they have given what? Constant angular velocity, that is 5 radian per second. Cylinder radius they have given, height they have given, gap is given, viscosity they have given. They are asking what will be the driving moment. Driving moment means what? Driving torque, we can say. Driving moment, you can say, or you can also say driving torque. Driving moment, you can say, or you can also say driving torque, that has to be there for rotation of the inner cylinder in Newton meter. Rounded up to what? We have to find it out to 2 decimal places, right? Now, so first of all, I'm just taking the figure out. This is rotating with some velocity angular velocity called omega radians per second. That is, they have given in the problem like 5 radian per second. They have given very clearly 5 radian per second. Now, if you just draw the velocity profile in between the gap, if you just draw the velocity profile, now the gap has been given in the problem, and in the gap they have mentioned that they are making what? Linear velocity profile. In the gap, they clearly mentioned that it is making what? Linear velocity profile. The velocity profile between the gap is what? Linear velocity profile. And the gap they have mentioned is what? H. They have mentioned in the problem is what? 5 mm. Again, we can verify 5 and 5, right? Viscosity of the fluid, they have given 10 to the power minus 4 Pascal second. There's no problem in that, right? Now, first of all, we need to just find the torque. You know the torque formula. Torque value is basically what? Force into radius. What force? Viscous force. Viscous force into radius. This will be the formula. Now, how to calculate the viscous force? How to calculate the viscous force? You know that the viscous force can be calculated as shear stress into area into R. What is the shear stress? You know that from the Newton's law of viscosity, the shear stress is directly proportional to angular deformation rate or directly proportional to velocity gradient. Now, if you remove the proportionality, you will be calculating as du by dy. What is the du by dy? In the problem, they mention very clearly, if you read the problem, they mention in the problem that whatever the velocity profile in the vertical gap between the cylinder can be assumed to be linear one. So V by H we can write directly. From the similar triangle, you can just calculate. So you can write tau to be as mu into V by H. The same thing I'm writing over here. Torque can be calculated as tau mu into V by H. Area, what is the area? Pi d into L. Pi into 2R into L. Whatever the length of the cylinder, vertical length of the cylinder into R. Again, torque formula, I can write something. Mu into what? What is the velocity? Velocity will be equal to what? R into omega. right? R into omega into what we can write 2 pi R square into L divided by H. So torque will be equal to 2 pi mu RQ into L divided by, into omega divided by what? H. Again, remember the formula like anything, 2 pi mu RQ into L into omega divided by what? H. H is nothing but the gap between the what? Inner cylinder and outer cylinder, right? Now, put the value. If you just put the value 2 pi into mu, 10 power minus 4 into R. R is given 1, 10th is given 2, omega is given 5, gap is given what? 5 into 10 power minus 3. If you just try to calculate this thing, that is 2 into pi into 10 power minus 4 into 10 into 1000 divided by pi. So you'll be calculating at 1.2566. But we have to round off to what? 2 decimal place. So it will be 1.26 Newton meter. So they might be given the range something called 1.24 to 1.28, something like that, right? So this will be the answer for this particular torque problem. You say torque, you say movement, both are same thing, right? So what will be the answer for this question? 1.26. So if you just try to observe the pattern of this year, in fact, the weightage is quite high as compared to the previous year. So that's why we just usually say in the course that never neglect any subject, right? We never know that how what will be the weightage, because they have not mentioned in the syllabus. Of course, they have mentioned in the syllabus all the particular courses, all the modules, but what will be the exact weightage, they will never going to disclose. In fact, if you just focus on the next year also for the paper, it's not guaranteed. It may be the possibility that the fluid mechanics, they will ask only for 3 to 4 marks. They will try to allot this remaining 4 marks with some other subjects. So that's why reading the fundamental for each and every subject is very much required, right? So I hope that you got the solution for this year that has been given for this fluid mechanics. So thank you all.